Okay, yeah, get excited because what we're going to do is we're going to link 4a, what we did at the start of the unit, like this 4-lesson unit, it's not that long ago, with what we've just done, definite integrals. So right at the start of the unit, we were drawing these lines and we were drawing rectangles under the curve. And we were approximating the area under the curve using lower rectangles and upper rectangles. So we did that. Now we're going to see the connection of that skill with definite integrals, because the definite integral from A to B is the area under the curve from A to B. That's what the definite integral means. So if we look at 4C, sorry, I've got one example typed out for you already. Find the area under the curve from y, the curve, y equals x to the 3, from x is 1 to x is 3. All that is the integral from 1 to 3 of the function x to the power of 3. And you can see we've evaluated that there. Okay, let's do B, but I'm going to just change B a little bit. We're going to change the function and we're going to change the boundary. And the reason we're going to do this is because when we did exercise 4a, the line we did was y equals 2x plus 1, and the boundary we did was from 0 to 2. So when we did exercise 4a, this was the function over which we were doing lower and upper estimates for. And I just want to demonstrate to you that our calculation is going to lie within those estimates that we performed. Okay, so we are asked, find the area under the curve, and then we're changing it. We're changing the line from 3x plus 2 to 2x plus 1. Okay, so that's the new function we're doing, and we're going from 0 to 2 rather than from 0 to 5. So what does this mean mathematically? All right, it means find the value of the definite integral from 0 to 2. All right, the point furthest to the left goes first, the point furthest to the right goes second, and our function is 2x plus 1, and always with regards to x. Okay, the first step, integrate. All right, so integral of 2x becomes 2, hangs out, x is x squared on 2. Okay, it's x to the power of 1, it becomes x squared on 2. And the integral of k is kx, integral of 1 is going to be 1 log x. From 0 to 2. Start in our numbers. We have 2 times 2 squared on top of 2 plus 2. Okay, now there's something I want to stress here about what you're required to show and what you're required to do and so forth. All right? So when we're using the fundamental theorem of calculus, okay, we're looking for the integration, we're looking for the substitution, and then all we need is the answer. Now, this is going to be particularly useful in our folio, is I don't want you to type that into your calculator, because look at all of the syntax you have to type in. It's enormous. You can simplify it a little bit, all right? And this one's actually not too hard to calculate manually. But for all problems involving definite integrals, don't waste your time typing that in. Just type in that, okay? Because that's going to give you the same answer, and it's going to definitely be right, even if this part, you made a small error there. And the more syntax you put in your calculator, the more likely you are to make an error. So anyway, when we evaluate this, what's that going to be? 4 plus 2, 6. Okay? And if you think, or you can flick back to 4a, when we first did our lower and our upper estimates, our first estimate was that the area was between 4 and 8. And we even made a geometric argument as to why the area is 6. Now, one thing, whenever the context is area, we need to put units squared, okay? So there's a difference between just evaluating a definite integral and a definite integral that has the context of area under the curve. Okay, so that's the first one there, that's the link that we're making. So in 4C, we're only doing question 4 and 5. Question 4 is about this skill, but I've got one more thing I need to show you, and that's what we're doing in question 5, which is a number of proofs. We haven't done many proofs yet, so we'll go through one, maybe 2 of these. We'll see how we're feeling. Any questions about that, the link to area under the curve? Good. So, prove that. Okay, prove that this is true. Prove that the integral from a to b of k is equal to k times b take away a. This is what we are required to prove. So, whenever we're required to perform a proof, what we're trying to demonstrate is that the left-hand side of this equation is equal to the right-hand side. So we can start wherever, it doesn't matter. I'm going to start with the left-hand side and I'm going to manipulate it. All right? So on the left-hand side, this is the statement that we have, isn't it? We have the integral from a to b of k with regards to dx. That's what we have on the left-hand side. We can simplify this. We know what the integral of k is. Whenever you integrate a constant, it becomes kx from a to b. Okay, this becomes k times b. All right, so I sub in the upper boundary, take away k times a, I sub in the lower boundary. All right, so all we're doing for these proofs is applying the fundamental theorem of calculus. I've taken my left-hand side, I've manipulated it, I've subbed in the upper and lower boundary, and now I'm just going to factorise k. All right, so we took the left-hand side, here it is, we juggled it, we've manipulated it, we've factorised, and that's the same as the right-hand side. We have established, it is true, the left-hand side is equal to the right-hand side. Now we're going to go through one more because you'll see on the right there, I might get you just to look at this one that we do, the next one that we do. On the right there we have other properties. Okay, so let's do the second one. I'll go through it, you can write it down if you want to, but we've seen this property a bit. If we have k times f of x, I've said that is equal to k times the integral from a to b of f of x. Alright, so the k inside the integral, the k outside the integral. Let's perform this proof. We'll start with the left-hand side. Might make some more room. Alright, over here, I'm going to start with the left-hand side. Now, all we're doing with proofs is just take what you've got and do what you can with it. So we have k times f of x. Now, we know if I have a number times something I'm integrating, the number just hangs out, right? So this is going to become k f of x from a to b, which is equal to k times f of b, take away k times f of a. Okay, now we might get to this stage and you're like, I'm not really sure how to make the left-hand side equal the right-hand side there. And that's perfectly okay. What we'll do is we'll go, okay, I'm going to stop there. I'm going to now jump over to the right-hand side and see what can I mash over here, what can I manipulate over here, to see if I can demonstrate that they are equal at any stage. Okay, if we can show they're equal at any stage, we've demonstrated the left-hand side is the right-hand side. So on the right-hand side, this is what we have. So always start with what we have, and then just perform the fundamental theorem of calculus. Okay, the k's hanging out. The integral from a to b of f of x, by definition of the fundamental theorem of calculus, is that the k is just hanging out. Okay, and then still the k is hanging out the front, and you might start to be able to see it now. Just applying the fundamental theorem of calculus. And there we go. left-hand side and right-hand side are the same. So when you're performing a proof, okay, all you're required to demonstrate is that they're both the same. You don't have to start with the left-hand side and arrive at the right-hand side. You can manipulate both and show that they're equal. We've shown that the left-hand side equals the right-hand side. And so what do we write when we've finished the proof? QED. All right, we've shown it's true. It has been demonstrated. So question 4 in this exercise is specifically about area under the curve. Question 5 is about the properties of proving the properties. Now I said when we're performing the fundamental theorem of calculus, right, we're sort of looking for 2 steps, you know, the integral statement, the substitution, and the answer. Okay. Just like all things, that is almost always the case. The exception is when you're asked to find an exact value of e or ln or a trig function. For all polynomials, so that's for all functions that are of the form x to the power of n, this is fine. Anytime there's an e, an ln, or a trig, you may need to simplify it manually, okay? But any roots, polynomials of that, just typing that into your calculator to spit out the answer for you. Very good. Okay, so let's jump over to 4C. We'll get everyone to have a go at question 4 and 5.